Yeah, thanks very much. We're delighted to have Thodoris Lykouris, I hope I said that right, here today. Thodoris is a postdoc at Microsoft New York in the machine learning group. And prior to that, he got his PhD from Cornell University, advised by Eva Tardos. And his research interests span machine learning, algorithms, optimizations, and economics. I know him best for his work on adversarial and robustness in Bandits and reinforcement learning. So it's great to have him here to talk about some of that stuff. Over to you.
Thanks, Kiara. And thanks also to both you, Gergely and Csaba, for inviting me to give this seminar, and also for organizing this wonderful seminar series. So today I will talk about corruption robust exploration in episodic reinforcement learning. And this is joint work with Max Simchowitz, who is a PhD student at UC Berkeley, Alex Slivkins, who is a researcher at Microsoft Research, and Wen Sun, who is an assistant professor at Cornell University. And feel free to interrupt me at any point to ask any question that is arising. Okay, so this talk will be about reinforcement learning. In reinforcement learning, we have a set of states. And for example, in this example, we have a state S0 to S8. And we have a set of actions. And for the purposes of this example, we're going to have two actions. One will be red and one will be green. And now each state is associated with some reward. So as state S0 and S2, for example, have reward of 0, while state S1 and S3 give you a reward of a peanut whenever you go there. And state S8 will give you a bunch of gold coins. So ideally, you want to go to state S8 because this is where the gold coins are. But the challenge is that you don't really know how to get to S8. And also, you don't know that state S8 is the one that has the gold coins. So there are also some state transitions that depend on the actions that you're selecting. If you are at state S0 and you select the red action, you're going to go to state S1. If you are at S0 and you select the green action, you're going to move to state S2. And although I described everything as deterministic, the rewards and the transitions can be randomized as well, and they can be selected from my ID distributions, both on the rewards and the transitions. Now, the goal in reinforcement learning is to try to find policies that map states to actions, such that you maximize the cumulative reward that you are aggregating across time. And there are two sub-goals on that. On the one side, you would like to exploit, which says that you want to maximize your reward based on the current information. While on the other hand, you want to explore because you would like to learn information about the rewards and the transitions and identify, for example, the state with the gold coins. And note that if you didn't know the state with the gold coins, then the red action here would be an exploit action, because at least it would give you a peanut, while the green action would actually be the explore action, because it would enable you to find out the existence of the gold coins. So this is a picture that we will have in mind. And this example will arise again when we will talk about the lower bound that has this version of anti-state rewards. Cool. Okay. Now the simplest possible setting of reinforcement learning is multi-arm bandits, where we have just one state and we have a finite set of actions. And the motivation of that is typically that you are in a casino and there are a bunch of slot machines. And whenever you select a particular slot machine, you're going to collect a reward, a randomized reward. And ideally, you would like, so the casino is rigged, so ideally you would like to find out which slot machine has the highest reward. You don't know that in advance, and you need to select the slot machines in a way to identify that. Now, what do we know about the setting? When we assume that the rewards are IID, this is the stochastic setting. This is a well-understood, well-studied setting in the last 30 years, and we have guarantees that are logarithmic in the regret. And I will define what regret means in the next slides. When we move away from the assumption that the rewards are IID and we assume that they are adversarial, we have worse regret guarantees of the order of square root of t, but still these guarantees are relatively efficient. Okay, so there is a gap between the stochastic and adversarial guarantees. Now, a very nice line of work that was introduced by Beck and Slivkins in a called 2012 paper was about the best of both worlds, which is a single algorithm that achieves the stochastic guarantees when the input is IID and the adversarial guarantees when it is not. So this is a nice line of work, and subsequently there have been many papers that have studied that. I just list these three papers because they correspond to different families of algorithms. But all these papers, with a small exception of the Selden and Slivkins paper, do not say anything about how it happens in the regime in between. And even Selden and Slivkins provide some preliminary and weak guarantees about this regime in between. So a couple of years ago, in a paper with Wahab Mirokni and Renato Paes-Leme, we studied what happens in between. What happens when the input is not completely stochastic, but it is mostly stochastic. And can you gracefully degrade with how much adversarial component will exist inside your data? So this model, we call it stochastic bandits with adversarial corruptions. We provide some initial guarantees that achieve this graceful degradation, and subsequently other papers have improved these guarantees. The Cold 19 paper has provide a refined regret guarantee, while the paper by Zimmer and Selden provide an even better guarantee for the weaker objective of pseudo-regret. So this is the state of the art in the multi-bandit land. We have a good understanding about what happens in the two extremes, and we know now what also happens in between. Let's move to reinforcement learning. So the simplest possible setting of reinforcement learning is the tabular setting, where you have a finite set of states, a finite set of actions, and a fixed time horizon 8. And now, whenever you are in a state, if I am in this state, for example, and I move up, then I will go to the state that is top of that. If I move right, I will go to the box, so I will stay in the same state. And if I go to a state that has a coin, then I will collect the coin. So that's the reward. So this is what the rewards and transitions mean pictorially. Now, what do we know in the tabular setting? We know in the stochastic regime, we have optimal guarantees with respect to regret. And there is a series of papers that refine these guarantees and extend it to provide better improvements. And now in the adversarial case, when we are in the expert setting, there is a paper by Ventar, Kakad, and Mansour that provides guarantees when the rewards are adversarial. And but the expert settings assumes that you have full feedback. So regardless of the action that you're selecting, you can see what happens in everything else. Now, when we go to the bandit feedback, work by Gergely and Csaba and others actually show how to deal with adversarial rewards when the transitions are known. And subsequent work by Jean et al. At the last ICML actually extends that to the case of unknown transitions. So we know how to handle adversarial rewards, but we do not, all of them assume that the transitions are IID. There is no, the transitions cannot be adversarially changed. Now, with respect to best of both worlds, the only result that we know is a result by Jean and Luo from these NeurIPs that achieves the guarantee of both stochastic and adversarial in the case that the transitions are known. And again, adversarial here means only adversarial rewards, not adversarial transitions. Now, this work will provide a reinforcement learning algorithm that will work both for the tabular and the linear MDP setting that will allow to handle both adversarial corruptions to both the rewards and the transitions. So we will achieve guarantees that will gracefully degrade from the stochastic regime when there is some adversarial interference in either the rewards and the transitions. So there are 3 points that I want to mention. So unlike previous work, we handle some amount of adversarial corruption in the transitions, which is, I think, is the first result that that is handling that. We also provide guarantees that degrade, that move away from the stochastic regime, even achieving the logarithmic regret guarantees when there is the stochastic. And also, it is the first result that talks about linear MDPs when you have bandit feedback in some adversarial regime. So this is a high-level presentation of the results. If there are any questions about the high-level description, that would be a good time to ask. Otherwise, I will move to defining things more formally.
No, I think it's all good. It's all very clear.
Okay.
At least here. And There's no questions in the chat, so you can just go ahead.
Cool. Yeah. Cool. Okay. So the episodic reinforcement learning protocol is the following. We have k episodes, and each episode has a length of 8 that is also called the episode horizon. And the number of rounds is the number of episodes times the length of the episode. Now we have unknown distributions for both the rewards and the transitions. And these three distributions correspond to what reward you will get if you are at a state and you select a particular action. And now the protocol works as following. At every episode, the agent commits to a policy pi k that maps states to actions. And now this policy can be randomized in principle. So we could be selecting a distribution across possible policies. Subsequently, a state is drawn IID from a fixed distribution. And at every step, the agent selects an action based on the policy that they committed to. They earn the reward associated with the state action pair, and we will assume that the rewards are between 0 and 1. And also they move to the next state based on the transitions P that are also fixed IID. And in the end, the agent observes the so-called bandit feedback, which is the state, action, and reward trajectory for the whole episode. So this is the classical episodic reinforcement learning protocol. Now, what we would like to maximize is the cumulative reward. So we would like to select policies pi k that maximize the cumulative reward. On its own, this quantity does not really tell us how well we're doing, because maybe we see a particular value on the reward because we really identified the best policy, and therefore we were able to get this reward. Or maybe all the policies have at least this much reward, and we did a poor job in finding a better policy that would have more reward. So typically in online learning and in reinforcement learning, one needs to compare to a benchmark, and the typical benchmark is the notion of regret that compares the reward that we are accumulating to the reward of the best policy. And the best policy in this IID setting is the policy that has the highest expected reward. So if I knew in advance the rewards and the transitions, I could compute what policy has the highest expected reward, and regret captures how much I'm losing by the fact that I'm acting at the face of uncertainty, and I do not know the reward and the transition distributions in advance. And for this regret notion, actually, there are many nice results that achieve regret that's sublinear in T. And in particular, for the tabular setting, for example, it achieves regret that is polynomial in H and square root of SAT. And the dependence on SA and T is actually optimal. The dependence on H is also optimized by these results, but we are not going to focus on the dependence on H in this talk, and we're not going to be optimal with respect to H. And examples of such algorithms are the UCB-VI algorithm of Azar, Osband, and Munost, that's a typo, and Q-learning by Jean, Alenzo, Bobek, and Jordan. Cool. Okay, so the episodic reinforcement learning setting, as we discussed, an agent commits to a policy, and subsequently they select actions and collect rewards and move to the next state. The only change that we're going to make in the model is that we are going to allow an adversary to corrupt the reward and the transitions in particular episodes. So initially, after the agent has committed to a distribution across policies, an adversary can decide whether to corrupt the particular MDP. If they decide to corrupt, then the new reward and the transitions can be arbitrary, subject to the reward being between 0 and 1, and the transitions also being the distribution. And if they do not corrupt, then we are in this green scenario where the rewards and the transitions need to be exactly the same as the IID setting. So note that this model, and subsequently, I guess, the rewards that we're collecting are the corrupted ones, and the transitions, the states that we're moving are based on the potentially corrupted transitions. These are corrupted if the adversary corrupts, and they are IID otherwise. Now note that if the adversary decides to corrupt 0 episodes, we are in the completely IID setting, because we will always behave according to the original reward and transition distributions. But if the adversary corrupts all the episodes, then we could be in a completely adversarial setting. So our goal is to try to adapt to the corruption level. So we would like regret guarantees that adapt to the number of times that the adversary corrupted. And I will refer to this as the corruption level of the adversary. Now, the goals would be to do as well as the best policy when there is no corruption. So we'd like to recover the stochastic guarantees when there is no corruption. Achieve a degradation in performance that is graceful with the amount of corruption. And I would not like to assume that I know how much corruption will exist in advance. So I would like to be able to have guarantees that automatically adapt to the corruption level without knowing how much corruption will exist. And ideally, I would also like to have high probability guarantees. And we're going to achieve such guarantees, although pseudo-regret guarantees are also fine. That's of less importance. And one side comment that I will not focus on much is that there are 2 possible objectives that one may care about here. The one objective is the corrupted objective that takes into account the corrupted rewards. And the other objective is the uncorrupted objective that disregards essentially the corruption when evaluating how well you're doing. And for different applications, different objectives make more sense. For the purpose of this talk, they're going to be equivalent because they are at most C times H away from each other, and we are going to be linear in C anyway. But generally, the guarantees that you can achieve even in Bandits are different with respect to the particular objectives that you care about. And in the open questions in the end of the talk, I will discuss this in a little more detail.
So Thodoris, there was a quick question in the chat regarding these corruptions. So like these corruptions are supposed to be bounded. So when the adversary changes the reward, is it supposed to respect the same rules as the original reward, or?
Yeah, that's a great question. That's a great question. They need to respect the rewards to be between 0 and 1, and the transitions need to be transitions. So they give another MDP that is of the same family. And in fact, it is an interesting question, actually, how you can deal with abrupt outliers that will not respect these things.
Yeah, but I guess if you have some extreme outliers, that just sort of makes dealing with corruptions easy, no? Right? Because if you see like some ridiculous reward, then you can just automatically ignore it, right?
Yeah, sure. Yeah, cool. Yeah.
Right.
But I guess in Bandits, actually, we know how to deal with heavy-tailed, for example. But the techniques will not apply to this setting, for example.
I see.
In Bandits, we have this RUCB algorithm, for example, that deals with heavy-tailed distributions. And this would be interesting, actually, to think about. Yeah. Okay.
All right. Gotcha.
Cool.
Thank you.
Okay. Cool. Okay. So the main result will be that for the tabular setting, we're going to achieve the stochastic guarantees time multiplied by the corruption level. So the stochastic guarantees are square root of SAT by Azaros, Bandit, Monos, and also logarithmic guarantees based on Simchowitz and Jameson based on some notion of gap with respect to Q functions that is not important in this talk. We are getting the same guarantees times C. So we achieve the stochastic guarantees when there is no corruption. We gracefully degrade with the amount of corruption, and we do not assume that we know how much corruption, and also the guarantee is high probability. Now, a caveat that I want to mention is that the guarantee becomes vacuous when C is greater than square root of T. Because if you replace C by square root of T in this bound, then this will become T, so essentially you get linear regret. However, even this actually is not trivial, and existing approaches will fail even with a logarithmic corruption. And as I will discuss in the end of the talk, there are many interesting open questions about what is the correct bound that one can get in this setting. And subsequently, we also extend that to the linear MDP setting, and we give similar results that take the best guarantee by Jin, Yang, Wang, and Jordan, and extend that to the corruption setting. And generally, both our algorithm and our analysis are completely modular and do not assume that we are in the tabular and the linear setting. The particular setting only comes in the end when we need to bound a confidence sum. So in particular, the algorithm, you can define it, you can extend it to other settings that we have that we will have stochastic guarantees in the future. So it is a general framework to robustify stochastic guarantees to corruption. So this concludes the part that I'm presenting the results of the talk. I will now move to the technical part of the talk, but if there are any questions about the results, that would be a good point to ask.
Yeah, so there's some discussion in the chat regarding the importance of this assumption that you make, that that the adversary actually replaces like the usual MDP dynamics with another MDP. So is it important actually that it also uses like a valid transition function, or could it just like produce like any sequence of states, or can it change the state space as well? Well, I guess if the state space is changed, then it's like also easy to catch, right?
Yeah. And I guess I'm not sure what it means to replace by a transition that is not distribution, because you need to behave according. The new state is not going to be generated based on that, right? So
yeah, right. So that's what I'm thinking, that since you allow like different transitions for every H, right?
Yeah.
Then like any sequence of states can be realized by some MDP. So it's really not a restriction.
Right. Yeah.
Also, there was some questions about the regret and the adversary, the part of the adversary where it's the adaptive adversary or oblivious adversary. I tried to make up some answer, but maybe it's better for you to answer it.
Yeah, the adversary is adaptive. So the adversary knows what happens in all the previous episodes, does not know what happens within the episode. So the adversary needs to commit.
There is a strangeness with the regret, right? So the regret is not going to be the corresponding policy regret, that like it's not a full game between the adversary and the learner, but it's this strange thing where like the regret is still defined with respect to the adapted corruptions based on what the learner was doing. Even though we are thinking about what could have the learner have done differently to achieve more reward, we're still thinking about the corruptions are produced on the trajectory of the learner.
Yeah. So I'm not talking about policy regret. I'm talking about the classical regret notion that evaluates what happens based on the sequence of rewards that actually were realized. The corrupted objective talks about what happens with the corruptions as well, but does not talk about the counterfactuals of if I did something different, I would move to some different.
A different corruption would have happened. That's not taken into account.
That's not what I'm. I'm evaluating based on the rewards, possibly corrupted rewards and transitions that ended up realizing. So that's the notion of regret, Cool. Okay. So there are generally two prior approaches that we're going to build on. The one is the UCB approach that is based on this principle of optimism at the face of uncertainty that employs aggressive exploration. And it's nice. It's a nice approach because most efficient episodic reinforcement learning algorithms actually build on that. But as we will see, it's not corruption robust, even in Bandits. So I will have one slide where I will explain what UCB does, and then I will show why, even in Bandits, this will be prone to a very minimal amount of corruption. Another approach is the approach of active sets that is used in algorithms like successive elimination, that is actually useful for corruption robustness. But as we will show, we are going to have exponential lower bound in reinforcement learning if you try to use this technique in reinforcement learning. And again, I will have one slide where I will explain how you can robustify Bandits by active sets. And then I will have another slide where I will discuss the lower bound. So the main contributions will be three. We'll have an algorithmic contribution, as we're going to suggest an algorithm that is UCB-based for reinforcement learning that incorporates active sets. And then we will have an analytical contribution that will have a framework that is beyond UCB for reinforcement learning. And we are going to apply these algorithmic and analytical contributions to achieve corruption robustness in reinforcement learning. And I should state that although we apply that to corruption robustness, the two first contributions can be useful even outside of corruption robustness, because there are other settings where you may want to have active sets. And so although I will present the results with respect to corruption robustness, both the algorithmic and the analytical framework are generic and can be applied to any setting where you're going to use optimism, but you also, for some reason, want to use active sets. Okay? So these are the main contributions. And the outline for the rest of the talk is that we will start from previous approaches. I will first discuss the stochastic bandits, the UCB algorithm, and the simple attack for small corruption level. Then I will show how in bandits we can make this robust to corruption. And then we will move to the contribution of the work, which shows the roadblocks to extend it to reinforcement learning, and then additional the challenges that we need to overcome and the key technical ideas in order to do so. So let's start with multi-arm bandits. So the scale that you see on the right corresponds to something between 0 and 1, which will say where the means of the rewards lie. And we're going to have two actions. The one action will be deterministic. So every time that you're selecting this action, you're going to reliably get reward 0.4, while the second action will be randomized, and with probability 60%, you're going to get reward of 1, and with the remaining probability 40%, you're going to get reward of 0. So the mean is 0.6. So ideally, you would like to select action 2 because it has the highest mean. So you would like to, it's better for you to select that because you're going to get a more rewarding expectation. However, the challenge is that you do not know which of the two has which mean. So one approach that you could try to use is to just select the action that has the highest empirical mean. So just get one sample from action 1, one sample from action 2, and then just go with the action that has the highest empirical mean. The issue with that is that if it happens that the reward that you're going to observe for action 2 is going to be 0 in the first round, which will happen with probability 40%, then you will only select action 1 from then onwards, because this is the action that has the highest empirical mean. So you will never recover, and therefore you will have linear regret, because with probability 40%, you're going to lose an expectation 0.2, which is the difference between the means of these two actions. Now, what UCB does is that it adds a bonus to this empirical mean. And instead of just selecting the action that has the highest empirical mean, you select a bonus enhanced highest empirical mean. And the bonus captures, tries to encourage exploration. It is of the order of square root of log t over number of times that you have selected the arm. So if you haven't selected an action frequently, then you will have a higher bonus. And the idea is that this bonus will be selected such that concentration bounds kick in, and the actual mean of each action will be below the upper confidence bound. So by selecting that, you make sure that you are always selecting something that has upper confidence bound higher than the actual mean. And after you have selected the actions enough times, the bonuses shrink. And at some point, what will happen is that the upper confidence bound of action 1 will be below the actual mean of action 2. And at this point, because we also know from concentration bounds that the actual mean of action 2 is below the UCB of action 2, we will never select again action 1, because its upper confidence bound will be dominated by the one of action 2. And since this will only take logarithmic number of times, this will mean that we will have only logarithmic regret. So we're only going to select the action 1 logarithmic number of times, and therefore we're going to have logarithmic regret. Now, what can go wrong when you have corruptions? One thing that I could do as an adversary is I could decide to corrupt every round that you are selecting action 2. And since UCB is a deterministic algorithm, actually I do know exactly which rounds you are selecting action 2. So maybe the reward is drawn by this Bernoulli distribution from action 2. But what I will do as an adversary is that I will always return a corrupted reward of 0. And initially that's fine, because you have a big enough bonus. So you anyway keep selecting action 2. But after logarithmically many rounds, actually the upper confidence bound will become pretty small and will go below the actual mean. And therefore, for the same reason why we were getting the logarithmic guarantee in the stochastic setting, we are going to show that we will have linear regret even with logarithmic amount of corruption in this corrupted setting. So this is why UCB on its own will fail at the presence of corruptions. Now, one thing that one could do is to say, okay, let's simplify the setting. Let's assume that we know an upper bound on the total corruption. Remember that that's not an assumption that we're going to make because we want to adapt gracefully to the corruption level, but let's assume for the time being that we know an upper bound C bar on the corruption. What we could do is that we could enlarge the confidence intervals to take into account this corruption. So even if the adversary was putting all the corruption against us, this extra upper bound will make sure that the actual mean of action 2 will be below the upper confidence bound. But in reality, we do not want to make this assumption because we do not want to assume that we know the corruption level. And there are two reasons for that. One way to ensure that you have such a corruption level is to assume a very loose upper bound, but then the regret will scale with that, so it will be inefficient. It will not gracefully adapt to the corruption level. And also, from a game theoretic perspective, if you know such a corruption level, and it's relatively small, what I can do as an adversary is just add a little more. So somehow, this is not desirable. You would like to have something that will adapt gracefully. So we want to deal with a setting where the corruption level is unknown. And for this talk, we are going to make a simplification that will actually demonstrate the key ideas on its own, that the setting is either IID or C corrupted for a non-C. And in the end of the talk, I will describe how this will extend to a general unknown C. So the setting is that we are in one of two worlds. Either we are completely IID, or we are in a setting that the adversary is corrupted by at most C, and we know C. And if the input is IID, we would like to get logarithmic guarantees. If the input is C corrupted, we would like to get guarantees that are of the order of C. Okay? And this will be just a simplification for this talk, but in the end, we're going to, it will help us illustrate the main algorithmic and analytical ideas. Cool. Okay. So the idea in my previous paper was that one way to deal with this setting would be to keep two algorithms simultaneously, one fast algorithm and one slow algorithm. And in both algorithms, we're going to enlarge them by log t. So we are going to make them robust to corruption of at most log t. And the idea is that we're going to keep local estimates. So whenever you're selecting the fast algorithm, I'm not updating the estimates of the slow algorithm. Whenever I'm selecting the slow algorithm, I'm not updating the estimates of the fast algorithm. Now I'm selecting the fast algorithm with probability 1 minus 1 over C. And the fast algorithm can be any bandit algorithm. UCB, Thompson sampling, whatever you want. It doesn't matter. The fast algorithm is just any bandit algorithm for the purpose of this talk. It is UCB. And the idea of the fast algorithm will be that it needs to fast enough, quickly enough, determine the best action if the input is stochastic. So it is responsible for the IID setting. Now the slow algorithm is more subtle. It will be selected with probability 1 over C, and its goal in life is to make sure that if the input is C corrupted, it will correct the mistakes that the fast algorithm has made, and it will allow it to recover. So that's the high-level view. Now let's see what happens in the two settings. If the setting is IID, then both algorithms have logarithmic regret. Because anyway, we just enlarge the confidence intervals by a logarithmic amount. The confidence intervals already had a logarithmic amount, so it doesn't really make a difference. The fact that we enlarged by a logarithmic amount, asymptotically, the guarantee is the same. So we just have two different algorithms. So we lose twice the regret because we have two different algorithms that need to independently find out what is the best action. Now, in the C-corrupted setting, the slow algorithm also has logarithmic regret because it is selected with probability 1 over C. The total corruption is at most C, and we keep local estimates. So every time that I'm using the slow algorithm, I am subsampling the corruption that it experiences. So in expectation, the slow algorithm is going to experience at most corruption of 1, and with high probability, it's going to experience corruption at most log t. And we already enlarged the confidence intervals by this log t amount, so it is robust to these violations. However, the fast algorithm is going to be prone to corruption, but for the same reason that we discussed before, because we are selecting it almost every time. And so the slow algorithm needs some way to supervise the fast algorithm, to correct for its mistakes. And now, the idea of how to do the supervision is by these active sets that essentially says that maybe the fast algorithm has converged to this bad example where it had eliminated the action 2, which is the best action, because we corrupted action 2 in the first rounds. But, and at this point, it's only selecting action 1. Now, the slow needs some way to correct this mistake, to allow the fast algorithm to recover. And the way that we do that in my previous paper is that the slow algorithm uses what's called active arm elimination, which selects actions uniformly at random until one of them is provably suboptimal. And at this point, whenever the upper confidence bound of the action 1 is below the lower confidence bound of action 2, it removes action 1 from the active set, and also it removes it from the active set of the fast algorithm. And therefore, it transfers the information that action 1 is not a good action. So the fast algorithm needs to start using the action 2. So that's the idea about how to deal with corruptions with active sets in the bandit setting. Now, the problem when you move to episodic reinforcement learning is that actually, if you try to do exactly the same idea, you will run to regret that it will be exponential in age. And this comes from a combination log example we have at the lower bound in the paper that is essentially the example that I described as a motivating example with the treasures and the peanuts. So if you try to use this idea of just selecting non-eliminated actions uniformly at random, you're going to have a logarithmic exponential regret in age. And this is because you don't do the aggressive exploration that UCB is doing. But the problem is that the efficient episodic reinforcement learning are UCB-based and heavily use this aggressive exploration. But the prior corruption robust algorithms are not. They use these ideas of active sets or some other ideas that are heavily not UCB-based. So we need to try to combine these two approaches. Now, the challenges that arise in this setting will be two. So again, we have the fast algorithm. The fast algorithm has converged on selecting the action 1. And now we need to design a slow algorithm that will be UCB-based, that will have some aggressive exploration so that it's fast, it quickly finds out what is the best actions. The problem is that if you just use UCB on the slow algorithm will decide that the action 1 has upper confidence bound below its mean, but it will not be confident that action 1 is indeed suboptimal, because it will stop selecting action 1. It will not wait until action 1 has upper confidence bound below the lower confidence bound of action 2. So the first issue that arises, even in bandits, is that UCB, because it does this aggressive exploration, stops exploring before ensuring that the action is suboptimal. So it cannot supervise the fast algorithm. The second issue that arises, and this only arises in reinforcement learning, is that now even if you fix that, the fast and the slow algorithm may use completely different trajectories. So it is not straightforward to have a good lower confidence bound for the best action of the slow algorithm in the trajectories that the fast algorithm is using. So now I will discuss how we're going to deal with these two challenges, and then I will describe the algorithm more formally. So the first challenge was this aggressive exploration. The fast algorithm has converged to action 1 by mistake. The slow algorithm has converged on action 2, but has not deemed the action 1 suboptimal, so it cannot supervise the fast algorithm. And note that we cannot just use the data from the fast algorithm directly to the slow, because the whole reason why the slow algorithm was robust to corruption was because we were subsampling the data that we're receiving. We were only counting them with probability 1/c. So the idea is that we are getting data points from the fast algorithm, but we need to use them in a way that is robust. So the first technical idea is that we are going to have some global empirical means as well for the slow algorithm, and we're going to enhance them with a C amount of a C amount. So we are not only going to have local estimates for the slow, but we're also going to have some global estimates, and we're going to take the minimum of the two essentially when we're considering the upper confidence bound. And this is how we will this will allow us to use data from the fast algorithm to eventually determine that the slow algorithm, the upper confidence bound of the slow algorithm will be below the lower confidence bound of action 2. And this will be precise in 2 slides. Now, this has dealt with a problem that the upper confidence bound of the slow algorithm was high, because now we use the data from the fast algorithm as well by these global estimates. But it does not really tell us that we have a good lower confidence bound for the slow algorithm in the trajectories that the fast algorithm is using. Because the slow algorithm and the fast algorithm may be using completely different trajectories. And in Bandits, this is not a problem, because in Bandits, we anyway have only one state. So we are actually going to select the best action for the slow. But in RL, the trajectories are different. So we need to ensure that the slow algorithm actually visits the same states with the fast in order to robustify them. Because otherwise, we're going to get, again, exponential guarantees. And the idea that we're using for that is that every step of our algorithm, we have some probability of switching to the slow policy and then rolling it out. This allows the slow algorithm to get robust estimates about the Q function on the trajectories that the fast algorithm is visiting, not only on their own trajectories. And so it refines this lower confidence bound. So the algorithm, more formally, is the following. We have the slow algorithm that uses both global and local data to find a robust policy. So the UCB of the slow algorithm will be the global UCB enlarged by a C amount, which is not a problem because we use all the data. So this will be OK. And it also has the local UCB that we were already using in the previous work to be robust to be robust on the data that we are seeing due to subsampling. And this global UCB allows us to use this, is the first idea that allows us to create a refined upper confidence bound for action 1 in the slow algorithm. And now the algorithm that the slow algorithm is recommending, which we could call supervised, and generally we call the algorithm supervised because it's a value iteration algorithm that supervises, so it is supervised. So the algorithm that the slow algorithm is recommending will be the algorithm, the action that has the highest slow upper confidence bound. Now, on the fast algorithm, we are going to supervise it by the slow. So we're going to create an active set that, based on all the actions that have slow upper confidence bound, not dominated by the lower confidence bound of another action. And the fast algorithm is going to recommend the action that has the highest local UCB based on, or restricted on the actions that are in the active set. So this allows us to make sure that we don't select action 1 in the fast algorithm after some point because it is removed from the active set by the slow. So the final algorithm for this fast slow setting is the following. At every episode, we start from a base algorithm, from a fast base algorithm. And then at every step, with some probability, we switch to the slow. This was the second idea, that to make sure that the slow algorithm robustifies the trajectories that the fast algorithm is visiting. And we're selecting the supervised action of the corresponding base algorithm. And we continue. Whenever you switch to the slow, you're going to stay with slow. So this is the algorithm that we're using. Now, on the analytical side, our approach essentially provides a novel Bellman-error decomposition. So the general idea in Bellman-error decompositions is that whenever you use a UCB policy, the regret at every episode can be bounded high level by the size of the confidence interval evaluated on the UCB policy in expectation. So that's a key part of the analysis of UCB algorithms. Now, the problem is that we don't use UCB algorithms. So we want to use algorithms that have a lower confidence bound that is not dominated by another upper confidence bound. And we provide a decomposition that essentially says that the regret will be upper bounded by the size of the confidence intervals evaluated on this policy pi k, plus a term that shows what would have happened if you started from pi k and you switched to the UCB policy. And the idea is that this switching would be with respect to the UCB policy of the SLOW, so it will allow us to connect the regret that we're getting with the aggressive exploration that the SLOW algorithm is using. And the key technical part is what we call visitation ratio, that says that in order to make sure that this is actually going to give us a good regret, we need to make sure that these expectations are not too far away from each other, the two density ratios. And the idea is that because we are switching from the policy pi k to the UCB policy of the SLOW algorithm with big enough probability, the difference between the two expectations can be bounded by 1 over CH in our case. And generally, when you can bound the difference between the density ratios of the two policies and you use this notion of active sets, lower confidence, you only select actions that have lower confidence bound higher than the upper confidence bound of your confidence interval, then we will be able to essentially turn the green quantity to rho times the red quantity. And this is important because the statistics that we have are with respect to the pi k. This is the policy that we run, so the states and the actions that we're collecting are with respect to that. Now, when we move beyond the simplifying setting, instead of just having one fast and one slow algorithm, we're going to have log t base learners, and we're going to deal with an unknown c. And the idea is that each base learner is going to have a global corruption level of 2 to the L and a local corruption level of log t. So the local corruption level would allow us to do subsampling and to be robust on our own data, while the global will allow us to do essentially what we did with the action 1 of the fast algorithm to use the data from the fast algorithm to correct the mistakes. And the pseudocode of the algorithm is pretty simple from that point. You start in the beginning of the episode with the most robust, with the faster and less robust algorithm, the layer 1, which you can think of it as the equivalent of the fast algorithm. And at every step, you switch to more robust layers. So you have an episode schedule where you switch to more robust layers. And in particular, you switch with this probability 2 to the L minus LH minus 1 over H. And you switch to layer L. Otherwise, you stay at the same layer. So what happens is that you only move to less robust layers, and then you use these active sets to find the action that each layer is recommending. So the first idea was this nested active sets. So instead of only having the slow algorithm creating active sets for the fast algorithm, now we have a nested active sets that start from the more robust layers and go up top to the faster and less robust layers. And the second idea, in order to have this visitation ratio, was to have a carefully selected episode schedule that guarantees that we are going to do subsampling. So we are not going to each layer with probability more than 2 to the minus L, but also it guarantees us that we are going to also also make sure that we have enough visitation ratio, that there is a big enough probability to switching to this layer and sticking to it. And the analysis, the way that we're going to use the Bellman-error decomposition is that we're going to use the UCB policy of the most robust layer, of the layer, the smallest layer that's robust. So the layer that is the log C, because that's the most refined layer that is robust to corruption. So to recap, the main contributions were algorithmic, analytical, and application. On the algorithmic side, we provide the UCB-based RL algorithm with active sets, and this allows to use any LUCB action, any action whose upper confidence bound is not dominated by the lower confidence bound of another action. And this can be applied beyond corruption robustness in other settings where you care about active sets, as long as we switch to the UCB policy with big enough probability. So you need to make sure that you have this visitation ratio to be bounded. The analytical is that we provide this framework beyond UCB in reinforcement learning that has this novel Bellman-error decomposition that allows to use any policy as long as you have the visitation ratio. So on the algorithmic side, we saw how to design such algorithms. And on the analytical side, we saw the Bellman-error decomposition that allow you to design it. And on the application side, we have these two ideas of nested active sets to make sure that more robust layers will refine the actions of the less robust layers, and also a carefully designed episode schedule to make sure that we have good estimates for the trajectories that the less robust layers are using. Now, this is part of a broader picture on trying to think about what happens between stochastic and adversarial cases. And as I said, this was started like a couple of years ago by my paper with Bahab and Renato in Maltian Bandits, and there have been refinements in Maltian Bandits. There are also papers that are tackling the linear bandit case, and there are interesting results in this direction, although we don't yet know tight guarantees for that. So this is an area that actually has interesting open questions. There is a recent paper, a new RIPS 20 paper, that does corrupted expert advice, an algorithm that interpolates between stochastic and adversarial when you have full information. Our setting was this episodic reinforcement learning setting where we don't even know adversarial transitions extreme. So this framework of adversarial corruptions allows you to discuss even settings when you don't have the adversarial guarantee and think about how to robustify that. So this talk was about tabular and linear episodic reinforcement learning. There are also works on assortment optimization that also we don't know the adversarial guarantee. Anupam gave a talk last week about secretary problem that also discusses what happens between stochastic and adversarial. And they have another paper that I'm very excited about with Akshay Krishnamurthy, Harapo Tumata, and Rob Sapire that talks about contextual search. And also this draws a nice game theoretic implication because we can think about irrational agents in behavioral economics terms, because this captures settings like pricing. So to sum up, we talked about reinforcement learning. We were interested about this interpolation between stochastic and adversarial settings. And the result in this talk that was that we provided a corruption robustness for tabular and linear MTPs. And there are a bunch of open questions. I'd only list a few here. One open question is to design algorithms that are non-vacuous for C greater than square root of t. As I already admitted in the caveat, our results become vacuous when C is more than square root of t. It is interesting to have guarantees that not become vacuous. In the bandit case, the work of Zimmert and Seldin gives square root of C pseudo-regret guarantee for the corrupted objective. Even extending that to non-transitions actually would be interesting. We know how to do best of both worlds for non-transitions. We don't know how to do square root of C. Going to best of both worlds, we know how to do non-transitions. The next step that we don't know is how to do unknown transitions. So that would be an interesting, very interesting next step. Any sublinear regret for adversarial transitions is for purely adversarial transitions would also be interesting. We only give for square root of the t. There are some lower bounds by Basiyat Kori and some others on this direction. So one needs to think about what is the correct level of assumptions that one needs to make in order to deal with it. And also, the technique was heavily rooted on the episodic setting and actually in the finite horizon episodic setting, because we had this layer schedule and we had the ability essentially to start a new episode afterwards. And it could be interesting. I think the techniques extend to the setting where you have reset, but it could be interesting to think about settings where this does not arise, like the stochastic sparse problem, or discounted settings that you don't have reset, or even actually its ability assumption. It's not completely clear how to deal with it. And I think that this would require fundamentally like new ideas, because our current algorithm is tailored to the episodic setting. Thanks.
All right, thank you very much. All right, that's some nice applause there. All right, yeah, that's great. So I was just, yes, there weren't too many questions in the chat, but yeah, I got a bunch of questions. It's like already regarding the bandit setting. I guess my first question would be: is this machinery with the slow and fast algorithm really necessary? Cannot you just use like a simpler algorithm like improved UCB, if you know what that refers to?
Yeah, excellent. Again, excellent. So you're describing the algorithm by Gupta et al. So Gupta, Koren, and Talvar are actually using a phased version of improved UCB, and they provide a guarantee that is additive. So it is C plus log T over gap rather than C times log T over gap. This was the COVID-19 paper. One thing about the fast slow and this multi-layering approach is that actually it extends to settings where you have continuous actions. So it is in the heart of the approach on the contextual search that I described. And for that, when you don't, it's not clear how to use improved UCB when you don't have a finite set of actions, for example. Because the improved UCB heavily uses the fact that you have gaps, because you're selecting based on the probability of the gaps. So it is, I think it's a more generic technique than improved UCB, but for the bandit setting, indeed, there are improvements that one can get by using that. This idea of fast, slow, and multi-layering can be applied more generally to other settings beyond bandits, I guess.
Right. Yeah.
And Simmer-Seldin is, we also provide the square root of C, is mirror descent with Charlie's entropy. So it's a mirror descent approach.
Yeah, that's right. Yeah, so you said that that if you want to do this kind of action elimination technique naively in an MDP setting, then you're going to pick up this exponential dependence on H. So how general is this argument, where you're just like looking at like one version of this action elimination algorithm, or like this fast and slow combo, and eliminating or like maintaining action sets and proving this exponential bound for that? Or were you trying to like improve the algorithm in other ways that you eventually did?
So the lower bound is for uncorrupted setting. There is no fast and slow. It's a pure uncorrupted setting, and the algorithm just says that you are selecting among, at every state, there are the actions that have upper confidence bound above the lower confidence bound of the other one. The definition of the confidence bound, I guess, is general. It's not very specific on particular, but the algorithm should look like that. Essentially, the upper confidence bound should want to be nominated, and you should be selecting uniform actions across them. So for that, you get exponential lower bound. So that's
right. Yeah.
The particular instantiation of what confidence interval means, I guess, is flexible, and I think one can be a little more flexible on how non-uniform, like going away from uniform, I guess, but like this is the main paradigm.
Right.
So this kind of says that this idea of just selecting random actions until eliminated, which is actually very useful also in the best of both worlds algorithm of Bubang and Slivkins, and in other settings, like I guess in contextual bandits, it is used as well. This idea on its own cannot extend unless you do something better. So that's why we combine UCB with active sets in order to deal with it.
Yeah, right. But well, basically the problem that I see there is that this seems to be somehow an inherent limitation of working just in the space of actions, so to say, right? That you make just these decisions about, yeah, I'm gonna like eliminate this action or put this particular action in the active set and remove some others from it, right? Instead of thinking in the space of policies, which is like really the eventual decision space, and trying to like compare and eliminate policies. Somehow, if you just work with individual actions, then you're probably gonna be ending up with this like exponential dependence on H.
Right. It's not clear. It's not completely clear, I guess, how you define active sets with respect to policies directly. I guess active sets are kind of well defined with respect to the Q functions of the particular actions. But I guess, yeah, I mean, I'm not saying that there is no other way that one can do active sets, but I guess it kind of makes sense to define active sets with respect to the Q functions of the actions, and that's essentially the algorithms that are using lower confidence bound and upper confidence bound in the sample efficiency reinforcement learning literature. That's how they work, I guess. So maybe there is another way. Maybe that's not the correct way to actually do that, but I guess it's not clear how to extend the action elimination techniques with active sets without that.
So there is there's a question in the chat. Giafan asked a question. Giafan, can you ask your question? He's trying. We can't hear you. Yeah.
Hi, can you hear me? Right.
Yeah. No, it's good.
Yeah. Can you turn back to the page about the upper confidence bounded algorithm with the corruption level?
Which page? Sorry.
Which page is that?
Yeah, you have say about knowing corruption level.
Okay. Cool. Yeah.
Oh, it's like
yeah, you said the problem is that maybe we cannot have a knowledge with the corruption level C, right? However, in case I think we can just set the corruption level as squared T divided S and A, and under this case, addition these bonus terms will not affect the efficiency of the upper confidence bound algorithm, and compare the result with your work. It seems that if the corruption level C is larger than squared T, then both the regret of the upper confidence bound algorithm and your algorithm will fail. And if the corruption level C is smaller than squared T, then there seems no problem with the upper confidence bound algorithm.
Excellent. Thanks for the question. So let me rephrase the question just to make sure that we're on the same page. Essentially, what you're suggesting is that if I set C bar equals to square root of T, then I kind of, anyway, I cannot handle more than square root of T. So I guess I'm having, I will deal with this, right? So the problem is that the regret will scale with C bar. So if you are in the IID setting, then you're going to scale with the square root of T. So you're not going to achieve the logarithmic regret guarantee, for example, when C is 0. Because when you have this known upper bound, essentially, that's why I'm saying about that if the upper bound is loose, then you have inefficient regret. Because you are going to scale with C bar. Essentially, this approach, because you have this upper confidence bound, the algorithm needs to wait until the upper confidence bound becomes small. So you need to select the action A at least C bar in order for this to actually become small. So this will scale with C bar. So if you set C bar to be square root of T, your bound even in the IID setting will scale with the square root of T. Does this answer the question?
You mean that if we set corruption level C is like square T, then the regret will become loose and the inefficiency.
Yes.
This is what you say.
It will not adapt with C, but it will scale with square root of T. Essentially, yeah.
Okay, my concern is that the original upper confidence bound, the regret is about squared SAT, right? And if we set the corruption level as squared T, then the addition bonus item C divide NA, and this item will not make the original algorithm become inefficiency. This is my point.
Yeah, let me try to add something to this. I think that Giafan is talking about the MVP setting, where you typically don't have the log T regret, but people would write the square root T regret bonds, like the worst case regret bonds. And from that perspective, what he's saying is correct.
Okay. So the bound is going to depend. The bound that you get with a non-corruption level, C bar, will be C bar times square root of T, or C bar times log T over gap. So if you set C bar of square root of T, you anyway get linear regret by this when you don't have gap, or you get square root of T over gap when you have gap. So in some sense, you don't, if it is the case that C is less than square root of T, C is 0, we are actually getting log T over gap, or we are getting square root of T. If you set C bar equals square root of T, in this approach, you are going to get something that will depend on the square root of T, I guess.
Yeah. If there is a gap dependent regret, then we cannot just set the as square T, right?
Yes. Right. I see. Yeah. But
Yeah,
it's
maybe in the general tabular settings, we can just set C as quality. And other case, it seems that your work is still efficient.
Yeah. So I guess just to make it clear, for the bandit setting, just ignore the MDPs for the time being. For the bandit setting, if you set C bar equals square root of t, you are going to be robust to corruption at most square root of t, and you're going to get a regret that is square root of t.
Right.
Okay?
Yeah.
Okay.
Right.
But in the MDP setting, actually, you don't necessarily directly get. You will only get this square root of t in this case. You're not going to get a logarithmic guarantee.
Right.
That essentially we are getting. We are getting C over log t over gap, and also it is not. It is not our approach, at least the way that it works in the MDP. You have multiplicative dependence on C bar times square root of t. So I'm not sure that actually it will give you even the square root of t result in the case that you have you set C bar equals square root of t.
Oh yes,
So,
thank you.
Yeah, for sure you don't get the logarithmic guarantees, which we do know in tabular setting, for example. We do know the tabular in tabular settings we have a log t over gap, and we do get these guarantees. And also the approach will give you to C bar times square root of t, so you will not get the square root of t. In bandits with non-corruption, you can get square root of t. But I think in RL, it is actually crucial to still do the supervision, and the supervision will give you something that will be multiplicative, even for non-corruption.
Okay, I get a point. Thank you.
Yeah, hi. I had a query on slide 84.
84. Okay.
Yeah. It was, there are two ideas presented. With the idea one was, I think so.
Sorry, what's the slide 84? No.
It's the beyond simplifying settings. Next slide, please. Next, this. Yeah. So on the second idea, the episode schedule, here we have 2 to the power L minus L H minus 1. So is this correct? Or?
Maybe. No, it should be opposite. Sorry. Yeah, it should be 2 to the. Yeah, it should be opposite. Yeah, it shouldn't. You should have a probability that is less than 1. Yeah. So it should be 2 to the L edge minus 1 minus L. Yeah, that's yeah. Yep. And that's why essentially when you start from the 1, you have 2 to the minus L essentially. Yeah. Thanks. Yeah.
Okay.
Cool. Thanks for catching that.
Yeah, and here you were actually like saying that that you start with the most robust version and just go less and less robust, but it seems to be somewhat the opposite to me, no? That you start with the fast algorithm.
Yeah, you start from the less robust and you go to the fast robust, the more robust. So you start from the faster algorithm and you stick with that because you want to quickly identify if the input is IID. You want to get the logarithmic guarantee in this case, for example. Right?
Yeah, right. Yeah. So that totally makes sense. I just understood at some point that you were doing the other way around, which was a bit confusing. But now I understand. All right.
So I have a question for this schedule. It's a bit weird that there is no feedback on this slide about the corruption level, right? So this schedule is just a priori, it's fixed random schedule. Do you have some thoughts about this? Like, is this? Yeah, I understand this is sufficient, but like, is this what we expect to see?
So the goals that this schedule tries to achieve are that we subsample the corruption at the robust layers, so they are robust. So you're selecting with probability less than 1 over C to make sure that the local log T will take care of that, and to make sure that the visitation ratio is bounded. So that's why it is sufficient. Now, it is not clear that it is necessary, and in Bandits it's not. I guess the improved UCB that Gergely was discussing actually does not have such a schedule, right? I guess it keeps the gaps of you select actions inversely based on the gaps that you have seen. So there could be other ways that actually you can do that. It's a little not clear. It's not completely clear whether you can like what possibly you could. One could possibly get improvements if they did a better schedule than that. This does give this multiplicative C. So yeah, it is possible that actually an improved schedule will get better guarantees. But I guess in some sense, for our analysis, we have like visitation ratio and subsampling, and the visitation ratio, and this is like our opposing force. You don't want to go to a layer with very big probability, because then you're not going to subsample the corruption. And you don't want to go with very small probability because it will not supervise the less robust layers. So this schedule essentially is tries to balance these two forces. But yeah, I guess the result I don't think is optimal. It's I don't think that you can only handle corruption square root of t. So somewhere I guess one needs to do an improvement. I guess maybe the schedule will be the place that one should do improvement.
Maybe there is some problems of similar type. There is a separation between adaptive and non-adaptive schedules, and maybe we have some form of that here too. But yeah, okay, thanks. That makes sense.
By the way, the algorithm is adaptive. I guess you do use the data.
Sure. I do have, of course.
Yeah.
But the schedule itself, it's just do this. You'll be fine. Don't look at the data.
Yeah. Yeah, because the properties that you're going to ensure are kind of non-adaptive, I guess. It's kind of like both the subsampling property.
It derives from the rest.
Mm-hmm.